Okay, just a minor correction for C. C is actually 4 divided by 3H2. These 4 and 3 are misplaced. Thank you. Okay, in this video, I would like to continue with the series on beam theories. So far, we have covered Euler-Bernoulli. We also covered the Timoshenko. And also we covered the Reddy. These theories start from a very simple one that we use extensively actually in engineering, as we discussed in previous videos, and uh, move to Timoshenko, which we have shear deformation, and then ready we have the shear as second order polynomial across the depth of the beam. This is constant shear across the depth of the depth of the beam. And then we discuss these three. One thing which is very common and can give us a hint of what we are going to do in this video and the follow-up is that in every beam theory, or each one that we have covered so far, we consider a kinematic. Let's say ui is u0 and w. We consider 0 to have the deformation in the plane of the beam, and we discussed that in general this is a function of x and z, considering our coordinate system, which always in all of the videos I use this coordinate system. This is along the x is along the axis of the beam and z is downward, and all the motion happens in this plane, and this one is a function of x. Now this one, for example, u for Euler-Bernoulli, if you recall, was z dw dx. So this z, which is the coordinates location from the neutral axis, multiplies by a function of x and a function of z. So here basically we come here, and if I want to write from a functional point of view, I call it a function of z and a function of x. And similarly for Timoshenko, we said that u is z phi. Basically in Timoshenko, phi is the slope. Actually in Euler-Bernoulli, phi is the slope, and in Timoshenko it is not necessarily equal. And in Reddy, we came and say that, okay, you have this z phi plus a cubic term, and we worked out the c, which is a constant, and gamma is the pure shear strain. So again, you see that in all of this phi is a function of x, phi is a function of x, and therefore our u is a function of z and x, on all of them. Now, if I look at here, I realize that there is a common approach to separate the functionality for z and x, and we know that x is order of L, length of the beam, and Z is order of H, height of the beam, or a typical dimensional value at the cross section. And we know that H over L, if I call it epsilon, is very small. And this slender ratio, if you like, justifies this separation. There is a mathematical foundation for that, that we justify this separation. In other words, we are saying that the the changes along the axis of the beam is much smaller than the changes across a cross section in the direction of z, shall we say. We are neglecting any displacement in the y direction, at least for now. And this is the whole background mathematical uh, foundation of beams, of a beam, a structural beam, I mean. A structural beam benefits from this. Basically, we go from a 3D to 1D structure. Otherwise, you can treat a beam as a 3D body and then consider all of the dimensions here. But in practice, we would like to use this geometrical fact, and then from 3D we go to 1D, and then basically all of these theories are based on this. So here we can say that why not set up a framework that by changing just one parameter, we could recover any desired beam theory. This is the whole background question or objective uh, of CUF, which is Carrera, which is the creator of this approach, Carrera unified formulation. So in other words, Carrera formulation or CUF is not a beam theory by itself, but it is an umbrella that it's a framework, it's an umbrella that can give you all of the beam theories from Euler, Bernoulli, Timoshenko, Reddy, and beyond. Any order that you want. For example, here we have linear term in respect to z, and here in Reddy we have linear term and cubic term. Why qubit? Why not z to power 5 or 7 or beyond? For laminated beam, which is not the discussion here, but for laminated beam, we need more than third order polynomial, and this is possible by CUF. So CUF is basically a framework that we are going to discuss in this video. Now, before going further, if I go back here and maybe change color, in Euler-Bernoulli beam theory, that we know that the cross section rotates about the neutral axis. So basically, this is a plane. Here it rotates as a plane, but not necessarily by the same slope at that point, by any angle, by phi. And here is dw dx, the magnitude of this rotation. But in ready, we will get a displacement that warps also, the plane warps, and maybe warps like this or like this, depends on the loading. And we know that we get the parabolic shape for the shear here. Here we get the constant for Timoshenko, we get constant shear, and here we don't get any shear. So this field, this variation of the plane normal to the neutral axis at the beginning is the whole topic of discussion in these beam theories. Basically, we guess or we assume kinematics, and then we try out based on our equation and constitutive law or kinetics or stresses, and check it against what it should be, as we did in the specifically in Reddy's beam theory. So CUF has this uh, flexibility that we can choose displacement, basically u displacement u to be of any desired order polynomial. In addition, this framework CUF is very suitable for coding. I mean, computer programming. Because you see here that by just changing one parameter that I will explain, you can actually recover Euler-Bernoulli, Timoshenko, Reddy, or any other higher order beam theory that you want based on your kinematics. So still the approach here is assume your kinematics and follow the kinetics map and see what you get and check it against reality or the physics of the beam. So this should give you the background for CUF, why we have this. It's not a beam theory, but this separation here is very important, or separation of the functions or variables, if you like, and the understanding of what is actually happening in each of these beam theories. Okay, If I come and write my u, which is the x component of my displacement field, w, we know what's happening in w, which is the deflection. And if I come and write my u as a polynomial, as the summation, I can use the Einstein summation coefficient, but let's be more clear. I give it a index k to n, z to power k by kx. If I want to relate this to my notation here, the phi x is my g function and my z to power k is my f function here. So I write my u, which is also, I should mention that u is a function of x and z, which we call it simply u. And it's clearly given here. And then if you expand this for few terms, for z1 becomes z by 1x. This is functionality plus z to power 2 by 2x plus z to power 3, 3x, and so on. Now, in this, we can immediately can see that if I let n to be 1, so k goes from 1 to 1, so I recover only the first term. And if my phi 1 is the slope at that point, therefore I get my u is minus z dw dx. This should look familiar. This is Euler-Bernoulli beam theory. Now, if I let again n equal to 1, that is the parameter that we mentioned. You could say k or n equal to 1, and therefore k is only 1. K is only 1. Let's put this in bracket. Then I get what? Then I get again z by 1x. But if I let phi 1 to be phi, then I get u is z phi. This should look familiar. This is Timoshenko. Beam theory. There is no longer necessary to restrict the phi to be the slope at that x location that we are considering. Now, if I come and let n equal to 3 or k equal to 1, 2, 3. So k should go from 1 to 3. Then I will get u is z by 1x plus z squared by 2x plus z cubed by 3x. No more dots because we stop here. We truncate it here. Here we truncate it here. We truncate it here. There is no an infinite series, but this is an infinite series. If I draw a box here, this is an infinite series. But for each beam, we make some assumptions, and based on our assumptions, we get a finite functionality or finite series that gives me the function. Now here, if you let phi 2 to be 0, and let phi 1 to be phi and phi 3 to be a function of, let's say, gamma, then you will get z phi plus, give it a constant here, c gamma. And if you recall, this is radius that we worked out. I guess we worked out that the c should be minus 3 over 4h square or something like that. Doesn't matter here for our discussion. And gamma is the pure shear strain. So this functionality gives you, recovers the radius. And that is why this is beautiful, because it can recover any beam theory that you might have or you might be interested. Now, you may ask, how do I know where to truncate? Where do I stop in the series that I have here? How do I stop? Where do I stop? Okay, that is something that we discussed briefly before, and that goes to that epsilon. This epsilon. If you have a very slender beam, let's say epsilon, let's give it some values here. Let's say epsilon less than 0.01% of the so basically the height or the cross-section dimension is about 1% of the length. Then you have a very slender beam, so n is good to have 1, and that will recover the Euler-Bernoulli beam theory. Now, if you go further and say, okay, how about if epsilon, sorry, if epsilon is somewhere between 10% and 1%, then you can take 1 again, and then so this is very slender beam, this is lightly slender beam, then you get the Timoshenko. With the condition that your phi is, I have explained already that the phi here for Euler-Bernoulli is the slope, but here for this range, you may need to go to ready, which is n equal to 3, or k1, 2, 3, as we discussed, and then you get your beam. If you have a less slender or deep beam, shall we say, and epsilon is between 20% and 10%, then you need to go higher, and then you need to go to n equal to 3 to 5, n equal 3 to 5. This brings highly nonlinearity in the cross-section in terms of warping and distortion, and we don't have a specific name for this, but this is by itself a theory. We can call it specific. And if your epsilon is, let's call it epsilon here, h over l, epsilon is larger than 20%, then you may get ultra deep or layered beam, multi-layer beam, and then you need to go maybe 5 to 9 terms from the series that we discussed. You see that very easily, and this is mostly for laminated beam or multi-material beam, very easily by adding terms to this or picking more terms of this series, you will add much more complexity to your beam theory, but sometimes it is necessary to recover the physics of the beam and how the beam behaves. And this is the beauty of CUF, Carrera Unified Formulation. For reference, I may give you a reference here, and that is the reference, you can say beam structures. And this is by Carrera and its co-workers. Is a publication by Wiley, and the year is 2011. So you may get this reference to one thing that I would like to say, that this book is it's comprehensive, and the notation is more on the computer side of the things rather than structural mechanics side of the things. But the essence I explained here, and that is all it is. So basically, what we are saying here, what we are saying is that at each cross section, we have a, maybe I mentioned this here also before closing the video. At each section, I have a amplitude, if you like, and I have a kind of shape function, if you like. I put it in quote unquote. So at each section, I get, for example, if I consider this one, I said this is linear, and this is my amplification. How much any material point located at Z on my plane perpendicular to my neutral axis will move. It will move by phi 1. How much that point, the same Z, will move as a as a quadratic or parabolic polynomial. This is this much. How much of it will go according to a third order or cubic warping? So these two are warping. This one and this one are related to the warping. This is any theory that assumes truncates here is plane remains plane. But how do we know? Maybe plane doesn't remain plane, and this is these two term comes in. These are warping, and the rest of them. All of them are warping, and but with different order. So as I said here, this will warp as a cubic. This will warp as a plane. Plane remains plane, but different rotation, and so on. And if you add more terms here, then you see that you're talking about very complex deformation of the cross section, but this approach or CUF approach can handle it. you may ask, okay, what happens if I go, for example, to three? What three we consider if I go to five terms and beyond? So you need some maybe experiment or some results from theory of elasticity to compare your results in terms of the shear stress and the normal stress due to bending and so on and so forth, or maybe from some very detailed experimental study that to see that what actually happens to the cross section shape after the formation. Okay, so that is this CUF. Uh, I thought to give it a try, at least some introduction here, and I discussed these three topics. So it's a very brief, but I hope this video helps you. If you go and get this book and read it, you will find it that it is not uh, an easy journey. I hope this video helps you to go deeper into that. So if you want to do programming for COF or when you want to do some calculation. Thank you.